Now we're going to take a look at some of the most basic and important properties and pairs associated with the Laplace transform. The first important property is the concept of linearity, and we're going to illustrate it through examples 4 and 5. Then we're going to take a look at the integration, in which integration in the time domain corresponds to 1 over s in the Laplace domain, and we're going to use example 6 to illustrate that, as well as example 7. And then we're going to look at the differentiation property, where a derivative in the time domain corresponds to a multiplication of s in the Laplace domain. And then finally, we'll look at the translation property associated with the s domain and in the time domain. Alright, so the first concept, linearity, is associated with the property of a system. Here, let me just read this through, and then we'll explain it further. So for statement A, the combined operation of amplitude scaling and summation precedes the operator h for multiple inputs. The operation we're going to perform, of course, here on the next couple slides is the Laplace transform. Statement B, the operator h, or Laplace transform, precedes amplitude scaling for each input. The resulting outputs are then summed to produce the overall output y of t. If these two configurations produce the same output, then y of t, the operator h, is linear. Here we have two diagrams to illustrate the concept of linearity. Here we see that the inputs, each individual inputs, x1, x2, all the way to xn, scaled by a1 all the way to an, are broken up and then summed here as a total. So that's our total input feeding into this operator transfer function h, and then the resulting is in an output right here. Or we can do another operation where we take each individual input, do an operation on that, such as a Laplace transform for each of these inputs. We get a corresponding result from this transformation, scaled by a1, same as here on the left. Then we add each individual outputs, scaled outputs, sum it right here, and we get an output. Now if these two outputs are the same for diagram A and diagram B, then we say that this operation is linear. And for this case, we're going to show that the Laplace transform is linear. And that's shown on the next slide here. Linearity. So here we have individual inputs f1 and f2 scaled by a and b, shown here. When you take the Laplace transform of this expression, we get a f1 of s plus b f2 of s. So each Laplace transform of each of the individual inputs. Here's a Laplace transform, substituting the definition so we can get the integral by definition of what a Laplace transform is. Since the integral is linear, we can break it up into two integrals, and now we recognize the expression for f1 of t here, and the expression associated with the f2 of here is the individual Laplace transform for f1 of s scaled by a plus f of 2 of s scaled by b. And that proves that the Laplace transform is linear. The inverse Laplace transform is also linear. In other words, that when we look at this, we get the same type of operation where we get the time domain description for each individual Laplace transform. So here's an example of linearity. We want to show that the Laplace transform for this f of t, were defined as a quantity times 1 minus e to the minus alpha t times this. Again, the step function is used to show that the integration limits is going from 0 to infinity. So the Laplace transform of this is given as shown here, a alpha divided by s plus alpha. Alright? So the Laplace transform of f of t, substituting f of t right here for this expression, yields the following. Since the Laplace transform is shown to be linear, we can break up this expression here into two Laplace transforms. And now we recognize that the first term here is just the Laplace transform of u of t, which we saw it was 1 over t. And Laplace transform for exponential is just 1 over s plus alpha. Okay? Now, so you get the individual ones scaled by a for each of these terms. So we have a over s minus a over s plus alpha. Combining in like terms yields the following expression, which is the result that we want here. Okay, this is an example associated with a sinusoid, and in this case we're going to say f of t equals a sine beta of t. And we want to show that the Laplace transform is this, a beta divided by s squared plus beta squared. In order to do this problem, we have to recall that Euler's formula, e to the j beta t is equal to the cosine beta t plus j sine beta t. We get a similar expression, except we got e to the minus j beta t is equal to cosine beta t minus j beta t. Now notice when you subtract this expression for e to the j minus j beta t from e to the j beta t, the cosines drop out and we're left with 2j sine beta t, and we can solve for sine beta t to get an expression just associated with the complex exponentials. So that's what we just did here. We substitute sine beta t for this expression here. Okay, so sine beta t is equal to e to the j beta t minus e to the minus j beta t divided by 2j. Now you see we got two parts, and we're going to use that property of linearity just to break it up. Alright? Now when we take the Laplace transform for beta t, we substitute each of these expressions there, and we recognize this is just a Laplace transform of an exponential scaled by a over divided by 2j. When we do that, we get for this one 1 divided by s minus j beta, and for e to the minus j beta t we got 1 divided by s plus j beta. Alright? And then putting it in common denominator here, we find that f of s is equal to s squared plus beta squared in the denominator, and a over beta is in the numerator, which is our desired result right here. So putting this expression again in a common denominator will give this result.